Okay, well, welcome everyone to 60 Minutes in Space, our last one of 2012. So thanks for coming back. I understand last time we had a major disaster, actually. So we apologize for that, but I guess there wasn't a whole lot we could do without power to the building. So yeah, we will do our best to not have a repeat performance tonight. So once again, welcome. I'm Steve Lee, the Curator of Planetary Sciences here at the museum. And tonight you'll have myself and Dr. Dimitri Klebe leading you through what's been going on actually for the last couple of months now, since we sort of missed last month. How many of you are here for the first time? Okay, enough of you that I'll just lay the ground rules. We each of us has our own areas of expertise. Dimitri is sort of astronomy and deep space things. I'm closer to home, typically Mars and human space flight and Earth-related things. So we each pick a fairly large handful of stories about what's been important in our areas of expertise for the last month, or two or three in this case, and go over them. And we'll encourage lots of questions, but if you don't need to have the question answered immediately, we'll have plenty of time at the end. If there's something that's really burning about a particular slide, go ahead and try and get our attention, and we'll answer it while the slide is up. So I think without further ado, I'll turn it over to Dimitri, and then I'll join you at the second half of the show.
Thanks, Steve. Just out of curiosity, how many people here were here last month? Okay, a good fraction there. Okay, that's good. Because the majority of my talk is going to be about what I was going to concentrate on last month, which is on dark matter. So I'm told that I got to move fast because we've got a lot of slides here we're going to be showing you today. So I'm going to get right into it. But the main thing I wanted to talk about was actually dark matter. I went to a conference in October called Dark Matters out in Chicago, and got my head filled with lots of good information about the whole field of finding what dark matter is. Today's cosmology, which is basically the understanding of the entire universe and its evolution, we have a good sense of what this universe is doing, but it does rest on these three mysterious pillars of dark matter, dark energy, and inflation. All of these involve big questions and eventually will involve understanding new physics. And my discussion's mainly going to center around here on dark matter. We think we've got a good handle on dark matter and that it's something that we're going to figure out what it is in this decade, basically. Now, I'm going to show you a video that was produced by NASA here relating to the Fermi Gamma Ray Telescope, but it's a good introduction to the field of dark matter here, and it also relates to the rest of my talk. So I'm going to put that on here.
For the past 40 years, astronomers have known that something about the cosmos doesn't add up. First in galaxy clusters, and then within individual galaxies, they found that visible matter, stars, gas, and dust, cannot account for the motions they observe. No one knows what this missing mass, now called dark matter, actually is. But studies by NASA's WMAP spacecraft of the cosmic microwave background, the oldest light in the universe, show how much is out there. Dark matter outnumbers ordinary matter by 4 to 1. The WMAP results also hint that dark matter likely takes the form of an as-yet undiscovered subatomic particle. WIMPs represent one hypothesized class of these particles. They neither absorb nor emit light and don't interact strongly with other particles. But when they encounter each other, they annihilate and make gamma rays. That's where NASA's Fermi Gamma Ray Space Telescope comes in. 2 years of scanning the sky with Fermi's Large Area Telescope have set the strongest limits yet for WIMP dark matter. The best place to look for gamma rays from dark matter annihilation? The most boring galaxies around, called dwarf spheroidals. These faint, tiny galaxies possess impressive amounts of dark matter, but they contain no gamma ray emitting objects and little gas or star formation. In the currently accepted cosmology, the first structures formed as the gravitation of dark matter corralled normal matter. Simulations show that the largest structures formed in this way were comparable to the dwarf spheroidal galaxies we see today. It's thought that large galaxies, like our own, were built up from collisions among these dwarfs. Using 2 years of data, Fermi scientists explored 10 dwarf galaxies for any sign of gamma rays from WIMP annihilation. In this graph, the dashed line marks the sweet spot where conventional expectations for WIMP dark matter align with what we know about our universe. Even when scientists combine all of the Fermi data from all 10 of the dwarfs, they see no sign of gamma rays. This limit shrinks the box where WIMP-based dark matter may be found, and, for the first time, shows that the cosmology we know essentially eliminates some WIMP types. The longer Fermi operates, the better its ability either to box in the nature of dark matter or to find actual evidence of what it is, and the discovery of new dwarf galaxies will make this search even more sensitive. Although nondescript, dwarf spheroidal galaxies may have been the first large structures to form in the universe. Now, they've taken center stage in the drama to solve one of astronomy's greatest mysteries.
Alrighty. Okay, so that's a really good introduction to the dark matter here. Now, what are some of the observational evidences that we know of dark matter? How many can see the title of this slide? Okay, I would argue that you don't. Okay, because you do not see the title, but you see what is influencing around it, and you can then actually figure out what it says. And similarly, that's how we actually detect dark matter in many ways. It was actually first detected by, proposed by Zwicky way back in the 30s, where he looked at the Coma cluster and saw that that cluster of galaxies was moving around at a faster rate than could be held together by the mass seen in the galaxies that composed it. So that was the first hint of it. We also looked at individual galaxies and saw that they were spinning at speeds that were indicative that there was a lot more matter there than met the eye. So the thing about dark matter is it doesn't interact with light and other particles, but it does have gravity. So it's the same in that sense as ordinary matter. And then a more recent technique in which we've been able to detect dark matter is looking at clusters of galaxies like this, where you see these kind of arc-like structures around the galaxy. Where those arcs are coming from is actually not from the cluster of galaxies, but from a more distant galaxy that's being gravitationally lensed by the cluster of galaxies, and that light gets bent such that you see little arcs of that same galaxy out there. And through that technique, we're able to look at clusters like this, look at these various arcs and things around it, and deduce how much mass is in that cluster and make an actual map of the dark matter. And so we see something like this for the same cluster that you saw in that previous slide, where the blue represents the distribution of dark matter in that particular cluster of galaxies. It's very evenly distributed. It does not form stars of dark matter or anything like that, because it doesn't interact with itself. So it forms these very diffuse halos around the clusters, as well as you'll find the individual galaxies having their own dark matter halos as well. And one of the best evidences of all, though, is actually a simulated result, in the sense, and you heard that alluded to in the movie here. This is an image of the cosmic microwave background radiation. It's the most distant light in the universe, represents the universe when it was about 1,000th its current size, when the universe was actually about the temperature of a low temperature star. And these variations that you see in the cosmic microwave background are very, very slight. They're only about 1 part in 100,000. And somehow, from this very smooth and even universe 14 billion years ago, we were able to evolve to our current universe that we see today, which is a what we often call the cosmic web. And it is this result where we can take these exact variations in the cosmic microwave, evolve the models to the current state, and see the universe we see today is very good evidence that that dark matter exists. If the dark matter did not exist in the proportions that we think it is, we would not have evolved the structure. We would not have any galaxies and stars that we see today. And we can actually, this is a picture of looking out at a slice at our universe, and we see that same kind of cosmic web-like structure. Now I'm going to show you pretty soon here an all-dome image of this cosmic web and the evolution to it. And the piece of the universe that you're going to see is going to be about 200 million light years across, which is very similar to this as well. This came out of the CLUES project, which stands for the CLUES. Okay, I got to remember again. The Constrained Local Universe Simulations project. And what's cool about this simulation project is it's constrained by how our universe actually looks today and the actual structures within that, because we want to compare it to the things that we see. So this is actually an image of a piece of space that is really analogous to what we see when we're looking out into the universe. The local group, which you see right here, is our local group of galaxies. The Andromeda, M33, and the Milky Way are these little groups here. There is the Virgo cluster right there. And in a larger image of these same simulations, just to get you in context where we're at, this LSC is the local supercluster, which is the Virgo cluster and the local group that you saw in the earlier slide here, plus the what we call the Great Attractor, the Coma cluster, and the Perseids Pisces cluster over here. So these simulations are actually simulating our real universe. So let me see if that's the next one. So that is what I'm going to do. So we're going to see a visualization of that starting from when the universe was about 1/50th its current size till now, and we're going to be more immersed in it here. So that's the cosmic microwave background radiation. That's not that. If you want to get rid of my slide, I don't know if that's easy to do. I probably shouldn't have written. Okay, there we go. And so in this simulation, it's going to be reversed to what you often see in simulations. The dark matter is actually going to be dark or black. It's going to start off very uniform and like this here. And you will see our current universe evolve from that. So we're looking at 14 billion years of time. Now the split screen here is showing you a much higher contrast version of showing you a higher, seeing more of the dark matter in that image. I'm going to play this one more time so that you can at least have seen this and then get to see it from the beginning again. It's only about a minute long. And then in the back here, they're going to do yet another split screen. Am I right, Greg? Okay. I just wasn't patient enough to see the last part of it. Now, when I was in Chicago, I got to see this, and they just showed it in the one contrast level. And one of the reasons they were actually going to this way of visualizing it is that they found a lot of people misinterpreting where the dark matter was. When they saw the inverse of this image, they thought that the voids were actually the dark matter. Here, the dark matter is the dark stuff that you see. So this top visualization you see up here is indeed what is normally presented in showing the dark matter, but in this case the light particles are the dark matter particles. This was done with 1 billion particles in the entire simulation, and they're just letting gravity work itself. So you can see where it starts off, where it's very, very uniform, and in fact, if you want to start it again, Greg, that'd be fine, and we'll just play the very first part of it from the start of the evolution. They are starting from the input parameters of what we knew the universe was like at that earlier time. And from that, you evolve this structure that we actually see today. I kind of prefer the lower contrast version there. You can see some of the filaments a little bit better. And so you might be asking, oh, the universe is expanding during this time. Well, what they do is they take a co-moving volume, basically. They're starting with something that's 200 million light years across in today's time, and it was about 50 times smaller at that time, which is about 100,000 times smaller in volume at the start of the simulation. So you're moving with that. So you're seeing the same chunk of the universe. Okay, I should move on here and put my slide back up there. Oops. We can go ahead and put the PowerPoint. Okay, so just to do the accounting and everything, when we talk about what the universe is made out of, you heard that dark matter is about 4 times more than ordinary matter. Well, we're talking about matter itself, but a majority of the universe is actually composed of this stuff, which I'm not going to talk about today. It was called dark energy. And if you even look at the ordinary matter, which is about 4% here of the total here, only about 0.5% of that is actually in stars. So the rest of it is really in hot gas, but it is ordinary matter. So the stuff that you and I are made of are a very small percentage of really what's in the universe. Now, what is this stuff? There is a whole slew of candidates for what dark matter might be. But at the top of the list, these things called neutralinos are the leading candidate. And I was going to just give you some insight as to what we think that is. A few months ago, I talked about the discovery of the Higgs boson, and I showed this particular image. This is the image of all the fundamental particles known to exist. You have your quarks, your leptons, and your bosons over here, 4 of them being the force carriers of nature, and the Higgs boson, the thing that actually endows other particles with mass, but it's actually not a force carrier. You're more used to these, well, you're not used to really any of these particles probably other than the electron and possibly the photon, which is the particle of light. We're used to protons and neutrons. Well, they're made of up and down quarks. So out of all these fundamental particles, none of them really exist much in nature other than the up, down, and electron. And we've got a few muons and things like that that are going around. And of course, a lot of photons and things. And the gluons are holding these particles together in the nucleus of an atom. Now, the standard model of particle physics, of which these particles come out of and everything and are predicted out of, also allows for the possibility that for every particle that you see on this chart, there is a supersymmetric particle. So those supersymmetric particles here, so every particle here, an up quark has all those quarks have their squarks and such. The Higgs particle has its supersymmetric one called the Higgsino. We think that one of these neutralinos is one of these particles, and we can rule out most of them based on the fact that we think the particle is a weakly interacting particle, which means that it only interacts via the weak force, which is the force that is carried by the W and Z bosons that are over here. So all the quarks, which interact via the strong force, the squarks can't be that. Anything that reacts with the photon, which is when we know dark matter doesn't react with a photon because it doesn't emit or absorb light, there are things that behave with the electromagnetic force. All of those can be eliminated. Anything with charge can be eliminated. So it doesn't leave actually very many particles left. It leaves the supersymmetric particles of the neutrinos, Not the electron. None of these are all charged here. One of these is charged. I always forget which one. I think the Z boson is charged. So the wino, the Higgsino, and the photino are the other ones that it could be. And the one we think it is the one that is the least massive. Because if it was more massive, it would decay into that particular particle. So that is the number one candidate, is a supersymmetric particle of the particles that we know to exist. One of the things I came out from the meeting that I understand better, that I appreciate better, is where did these particles come from? Well, where did any of the particles come from? Well, the answer lies, if you go back to the Big Bang, or close to the Big Bang, within a fraction of a second, the universe was really hot and dense at that time, and particles were morphing from one energy state to another. So every kind of particle exists. And as things started to cool down, they started to condense out of that quark soup, basically. Well, an interesting thing for ordinary matter, since it wants to react with itself, is that if we didn't have more matter than antimatter in the universe, all of it would have combined back here and we'd had no ordinary matter now. So for some reason, about one particle in every billion was an extra matter particle as opposed to an antimatter particle, and therefore we have a universe now that has matter in it. The same is not true for these weakly interacting massive particles, the WIMPs. They actually, since they barely react with each other, as things started to condense and freeze on out, eventually they got less dense that they didn't interact with one another anymore, and were frozen out. And we could have some WIMPs left today. And in fact, if you do the calculation, and to see how many WIMPs should be left for the day, you get an answer that is very close to what we have today. They call that the WIMP miracle, is that you look at the particle physics aspect of the Big Bang, and we really should have, if that particle exists, we really should have that many WIMPs floating around now. So that is a very interesting result, and the thing that I had picked up from this meeting. Now, so like I said, we're going to solve this in the next decade. So there is a serious hunt right now to find out what this dark matter particle is. And so in the movie, it referenced how the Fermi telescope is looking for dark matter by the annihilation that occurs at the center of galaxy. It's like our Milky Way galaxy. If we were to look out on the sky and look toward our Milky Way galaxy, this is how dark matter would be distributed. And therefore, if the dark matter, which is exists in its particle and antiparticle pairs, could annihilate itself and then emit gamma rays here, we could see them in the center. The problem is there are a lot of other things that emit gamma rays there. So a better source is actually to look at what the movie had suggested was these dwarf spheroidal galaxies that don't have much many stars in them and are largely composed of dark matter. So you saw from the movie that it's starting to push down those results and narrow the limit of where to find those dark matter candidates. Now, there's some other issues with the whole dark matter scenario, something they call the substructure problem. And I'm going to just show you this movie here, and there's a couple ways around it. But here's the cold dark matter simulations, of the same simulations that we just saw on the dome here. And you see there's a lot of other little things floating around the Milky Way galaxy, which is being simulated here. If the dark matter is a little warmer, in other words, it's moving a little bit faster, you see a little less of that structure. The problem is we don't see all of these satellite-type galaxies around the Milky Way. We see a few, but we don't see thousands of them like you see in that particular image. The other thing is, so people are looking at potential ways of getting rid of some of these. One possibility is that the dark matter is moving a little bit faster. Another thing is that it's possible that it's not the dark matter. Here's the same dark matter model. Here's what the gas is doing in that simulation. The gas runs into itself, so you don't see as many of these satellite galaxies in this simulation as you do for the dark matter. So what you're looking at here is gas, and what here is you're looking at is dark matter. So, but the possibility exists that there are lots of these dark matter halos out there that have no stars in there. So that's going to be an interesting place to look if we know where to point. So that's a tough part. Okay, let me move on. So the big hunt is actually happening in direct detection. We're trying to see dark matter run into ordinary matter and see that it produces some sort of signal. It's a very tough measurement to make, as I will show. And it's really just the billiard ball thing. A WIMP comes in, hits another particle, knocks out, hits that nucleus, and pushes it around, and we see its interaction within the body of material that we're looking at. So there, like I said, there's a whole bunch of experiments that are going on right now. I'm going to describe a few of them here, just to give you an idea of how much dark matter there is around and how much you have to work with. Here's again that image of the Milky Way and the dark matter halo. It's very evenly distributed. So if you were to look at how much dark matter is in this room, you would find about 1 dark matter particle per cupful in terms of volume. But in terms of its velocity and such, it's moving at velocities comparable to our velocity going around the center of the Milky Way. So there are a lot of dark matter particles, if they exist, streaming through our bodies as we speak. I mean, billions and trillions of them at a time. So we have a lot to work with. The thing is, they don't interact very much. If I threw a dark matter if I had an ocean of water between me and the nearest star, Alpha Centauri, I'd have a good probability the dark matter particle would hit one of those water molecules in that travel. But only if the ocean was as deep as the distance between us and the nearest star. So it barely ever reacts with anything. So where are they going to actually make these measurements? They're going down into deep mines. Here's the entrance to a mine in Minnesota called the Sudan mine. Here is an image showing all of the mines that are currently in operation here. I'm going to talk about, so the experiments, one is going to Sudan. The one I'm going to talk about, a story that happened, that did this month here, is happening in this Homestake Mountain. It's now called the Stanford Research Laboratory here. And the reason going down in the mines is to actually to reduce the cosmic ray and gamma ray flux that we're getting from outer space, so that is not what's running into our detectors. We have to really, really lower our backgrounds to make those measurements. So this month they just had an article here on this particular experiment called LUX, which is the Large Underground Xenon experiment. It's in this South Dakota mine, which they call the Stanford Research Facility. It's nearly a mile down underneath the ground. And I'm going to talk about this experiment because it really is a pretty cool one, and they think this one has a really good chance of detecting the dark matter particle. Basically, you have this 350 kilogram vat of liquid xenon, which to keep it at a liquid form, you have to cool it down to cryogenic temperatures. We're talking, several hundred degrees below 0 Celsius to get it to liquefy there. And then they have a series of these, what we'll call photomultiplier tubes here that are detecting that event. And I will show you a little movie as to how that event is actually detected. The other thing that they do with this thing is they submerge this in a big vat of water, because you also get the emission of radioactive decay elements from the walls down in the mine there in the ground that are going to influence your results. So you have to put it in this bath of water. So the thing that here is that tank down underground, and here's a view inside of it. And this month they got this thing filled with water. So it's getting very close. They want to have this thing operational in 2013. So now they're going to be testing all the electronics. All the electronics have, so they rely on these things called photomultiplier tubes, which you see around here, around the edges here. So these ones here are just to detect if I get one from these ones, I know that I've got it from the surrounding area, and that if I get an event here, it's not from a WIMP. It's from something in the neighborhood. So they're using that to reject things. So so in the projection chamber here, the WIMP comes in and hits something, and they're able actually to have more photomultiplier tubes here to detect that happening. So I'm going to show you the movie here that shows that happening. And you'll see over here that the WIMP is going to come in. It's going to hit the xenon particle. When it does so, you'll see that it will produce a little bit of a signal here and up here. It causes a release of electrons, which are then pulled toward this grid here, and then hit this luminescence grid and create a secondary signal there. So this is a really cool device that actually allows them to isolate where the event happened within the chamber. The other thing that it does, it allows them to discriminate what kind of particle might have hit. So here is the observations of, in this case, a neutron source hitting things, and they can tell the difference between that and electron recoil, which is caused by a gamma ray that would have come in there. So there's a different signal between the two. That's the whole name of the game, is how do you isolate your backgrounds, and how do you, when you do have backgrounds, how do you determine what is a real signal and what is not a real signal. So, like I said, that one's getting going. So the photomultiplier tubes are amazing devices. They can detect a single photon that comes in and hits them. And I've always wanted to show this slide, so I finally decided to show it here. But this is a different experiment called the Super Kamiya Kondo. It's for neutrino physics here. But this is totally lined with these photomultiplier tubes, and I kind of went backwards there, but these are a couple guys in a raft here servicing all of these, and it's filled with a big vat of this basically cleaning fluid. They recently had a disaster where one of the photomultiplier tubes exploded, and it caused a chain reaction, and they lost a third of the photomultiplier tubes in the whole thing. So there's that person. Another interesting experiment that's being conducted was talked about by Juan Collar, who was at the University of Chicago at this meeting and everything. And I just think it's a pretty neat result. They basically have a chamber of superheated fluid. And when a particle comes in there, you've seen that the case, like if you put in a microwave, you get water too hot and all of a sudden it flash boils. They've done something like this on Mythbusters, which it indeed does do that when you superheat it beyond its boiling point. Well, what happens is that when you take, say, something out of the microwave and you just give it a little bit of a jiggle or something like that, or drop something into it, then that causes it to boil. So they're actually doing that same thing in much larger vats here that is going to go down in the Minnesota mine. And what's really neat about this is a single WIMP particle causes a macroscopic effect of this boiling and everything that you can see there. So it's yet another one of the detector technologies that they're utilizing. Now, I won't spend too much time on this here, but basically they're trying to squeeze down, like the xenon measurement, squeeze down what they think the mass is here, and they believe it is somewhere in this range over here. Now I'm running out of time, so I'm not gonna, there's a result, a positive result that has been right up in here, but I'll spend another time to talk about that. But other experiments rule it out. Yet this person up in Chicago, basically, they're doing a similar measurement, and that's what this graph is here. There seems to be a hint that that signal really is there. So anyway, stay tuned for that. That'll be a major announcement if that is the case. But it will boggle the minds of all the particle physicists, because they don't think it could possibly be dark matter where this group has detected it. And some of you may ask, can they use the Large Hadron Collider actually to detect dark matter? And the answer is yes, they're going to be doing that as well. I talked about this when I was doing the Higgs boson stuff, but the Large Hadron Collider, you're basically running protons around at high energy and running them into one another and producing other types of particles. That's how they detected the Higgs boson. Well, the Higgs boson is detected in a way where you have enough energy to produce the Higgs boson, annihilates itself, you actually detect those high energy gamma rays from that, and you figure out that it had a certain amount of mass. In this case, the Higgs boson had a little bump here at 125 giga-electron volts. Don't worry about the units, but that's a representative of its mass there. But what would happen if dark matter was created? It doesn't react with anything. So what they'll see is a deficiency in the signal there, not so much from this particular instrument. So in other words, if you create dark matter particles in your Large Hadron Collider, they will actually just go out and not react with anything else after that. So you're looking at what they call energy deficits. Okay, so my last story here I wanted to say was they made a measurement. You know, we saw the thing on the dome here of the filamentary structure which the universe is actually made of. And we have now been able actually to measure filaments, our first filaments out there in the universe. This is a cluster of galaxies here, and by using the gravitational lensing technique, they have been able to reconstruct the mass in this cluster, and they've detected that there's a very long filament that's like 60 million light years across. And so here from that cluster, I'm kind of going fast because I see Steve walking down the steps, by the way. And they've been able to recreate the mass in this cluster by all these galaxies there by background galaxies. It's an amazing technique. And they've been able to also measure all the individual galaxies in here and find their redshifts and such to reconstruct the three-dimensional nature of this filament. So this other movie, so really this filament looks short on the sky, but you can see down here it's actually a much longer filament because some of it is along our line of sight. So this last movie here is actually just a representation of that in 3D, which is the first 3D filament that we've ever been able to image in dark matter. Another interesting result of this, if you look at the amount of mass that is taken up in the filament, if this is representative, it looks as though half the dark matter is actually in the filamentary structure that makes up the universe. Okay, Steve, I'll let you come on down here as they watch the end of this movie. All right, thank you. Oh, I did have one more slide, but I'll just put it on there. This is the latest Hubble Deep Field image here, but I won't talk about it.
Go ahead.
Oh, okay. He says, "Go ahead." Anyway, so the famous Hubble Deep Field image that was first made represented a point in the sky where there were no stars that they looked at for about 10 days. Then they redid that, bumping up the amount of day with a better camera when they called it the Ultra Deep Field. This is an image of what's called the Extreme Deep Field with the new camera. Is it called WIFPIC now? WIFPIC 3 camera, which has some better infrared sensitivity to it. And this is an image equivalent to about 23 days of Hubble time looking out onto the sky. And it's a very small portion of the sky. It's the image that if you extrapolate onto the entire sky, you get about 100 billion galaxies. Everything you see in that image, with the exception of that thing there, is a galaxy. That's a star, a faint star within our own Milky Way galaxy. But this is exciting stuff, but it just tells you how little of the universe that we've actually looked at. And it's exploring those larger and larger areas on the universe, trying to map, like I showed you in the previous thing, to the filamentary structure of the dark matter and the entire universe itself. So, okay. Here's that.
Okay, thank you, Dimitri. Now, we'll come back home. Maybe. All right, let's see what's going on here. There we go. All right, so it's been a little bit of time since I've done an update on the Mars exploration rovers. Opportunity is the one that is still operating, and you'll note that it is 3,145 days into its 90-day mission today. So it's still going strong. Just to remind you of where Opportunity is, it's right on the edge of Endeavour Crater, and it's been circling this hill called Cape York, right on the rim of the crater. And this is a closer up view of Cape York. The white line is the path that Opportunity has been taking. It spent most of its last winter over here, and since then it's been down in this area. This is called Matijevik Hill. Jake Matijevik was one of the main engineers that worked on the Pathfinder rover, Sojourner, and also on Spirit and Opportunity, and had a great deal of influence and work spent on Curiosity as well. And he passed away just about a couple days after Curiosity landed. So they're honoring him by naming this area for him. From orbit, this ridge is seen to contain clays, and so that's a very interesting feature that they're trying to see up close now with Opportunity. And this is the area that they've been circling around with Opportunity. And this is a false color view of the type of rocks they're seeing in this area. They see the normal stuff that they're used to, these little blueberries sticking out of the rocks, but then there's this rind of stuff sitting on top of these rocks, and they've been very interested in that. So they've been using the instruments on the end of the arm, the microscope camera, the alpha particle X-ray spectrometer, to try and determine what these rocks are made of. And the results are still being analyzed. So I can't give away any secrets since I don't know them. This is the microscope camera view, and you see this is sort of the background matrix of the rock, and then this, obviously this rind is something that's very different. It certainly has a very different texture, different color in the color images, and they're trying to find a big enough piece of it to analyze with the chemistry experiment, the APXS. And so that's all I'm going to say for the moment. Hopefully by end of January, when we come back for our next 60 minutes, we'll have some of these composition results in hand. When I say that they were excited about clay, the reason for that is clay minerals are formed in the presence of liquid water. And so that's when you have another type of rock and then it gets wet for a sustained period, it alters the composition and the structure of the rock. And so that's, that would be a very exciting type of outcrop to see. So this is just the summary of this mission now. It's day 3145. It's driven 35.43 kilometers, and that happens to be 22 miles. So it's been motoring along for almost 9 years now, and it's, well, motoring might be a bit of an overstatement, but it has been moving for that amount of time. And it's returned almost 175,000 images so far. Remember that number, the 175K, when I get to Curiosity, which we'll be talking about next. You'll see how much more data is being returned from Curiosity than these rovers have managed, even though they've been very productive themselves. So that's it for Opportunity, and I just wanted to show one image here looking back at Spirit. This is the last panoramic image that Spirit returned. These images were taken in late 2009, early 2010, and they've gone back and reprocessed this panorama so that they have much, much better views of, or a much better product. They've removed all the seams and done the geometry much better. And if we have time at the end of the program tonight, we'll come back and look at this panorama on the dome. If not, I promise we'll do it next time. So that's just looking back at Spirit. The last time Spirit was heard from was in May of 2010, so it has presumably perished finally after being on the surface for, I guess it was active for almost 7 years. Okay, so let's move on to Curiosity. And it's, actually I was looking back, it was the 19th of September is the last time we've talked about Curiosity in 60 Minutes, and that was only about 6 weeks after landing, so we've got a lot of catching up to do. Today is day 112 since landing, and I guess I'm happy to report that everything is working just splendidly on Curiosity. It's only got a couple of instruments, actually one instrument left to check out, and then it'll be fully operational. They have been doing a lot of science. And just to get it out of the way, because I'm sure a lot of you are going to be wondering, this flurry of news coverage that's happened in the last week, where the project scientist John Grotzinger was giving an interview to NPR late last week, and he made the statement that they've got some new results, and these are going to be results for the history books. And he said, I can't tell you any more than that. We'll announce it in a few weeks. And of course, the media has gone crazy, the blogosphere has gone crazy, Twitter's gone crazy, and NASA's gone crazy. So there's been some statements that came out of JPL in the last day saying, well, that's sort of been taken a little out of context. The entire mission is one for the history books. And so I think they're backpedaling a little bit. But the truth is there's a major geophysics meeting. The American Geophysical Union meeting is happening starting this coming weekend in San Francisco. And next Monday, there will be a session devoted to Curiosity. And whatever they have to say should be released on Monday. And I've tried prying it out of the folks that I know that are directly involved in the mission, and they all say, well, there's some interesting results. No, we can't talk about it until next week, and they sort of leave it at that. So that's all I know, and just to put that discussion to rest, check back in next Monday, and hopefully we'll know what's got everyone all excited. Okay, so let's catch up on some of the really significant things that have been discovered so far, and I would count this as probably the top finding in my book as a sort of a Mars geologist. These images were taken in, I think, early September as they were driving away from the landing site, and these rocks, when you look at them up close, and we'll look at some better pictures here in a second, but they look like they're conglomerates. There's a lot of small pebbles that are cemented together into these slabs of rock that have been broken. And when you look closer, there's cobbles, there's lots of small things, some big things. That's about 1.5 inches across or so. But what's really exciting is you look at all this gravel here that's sort of eroding out of these rocks, And when you look at that in detail, these particles aren't sharp and angular and really broken looking rocks. They're rounded, they're soft edges. And to any geologist on Earth, you would say, well, that looks like it's probably what's left over from a stream bed. And the way that you make rounded rocks is you carry them downstream in a flow of water, and they bang into other rocks, and sort of all the sharp edges and rough edges get worn off, and that makes them look like this. So what's significant about that is that's the type of stuff you see with a sustained flow of water, not just a single flood, but you've got water flowing for a long enough period that it's able to wear those rocks down like that. And that's the first time we've seen anything like that on Mars. From orbit, we've seen lots of evidence that there are dry riverbeds, gullies, alluvial fans, things that were obviously carried by liquid flows, but we've never actually seen this sort of thing on the surface that would indicate that those features took place over an extended period of time. And this is just another view. This is actually true color, what you would see if you were standing there. So all these things all cemented together, it really makes a very nice story. And this is the type of thing that you'd see on the Earth in an alluvial fan, where this is in the Mojave Desert, where every now and then you get a gush of water, you get a rainstorm up in the mountains, and it flows down and carries material with it. So that's what we think we're sitting on Mars right now. And this is Mars on the left, this is the Mojave on the right, and very, very similar structure to the rocks. So that was a really nice result. And I'll show you a video here where they can explain it a lot better and have some really nice visuals to support all this.
Mars Curiosity rover. This is your Curiosity rover update. We've now been on Mars for almost 2 months, and we've been witnessing the amazing new vistas of the never-before-seen Gale landscape taken with our wonderful cameras. However, much of the science team have had their eyes, and the rover's eyes, firmly focused on the ground. On the drive from the Bradbury landing site to our current location, we have been analysing 3 really interesting outcrops that we have called Goulburn, Link and Hotter. If we look at the Hotter outcrop, we can see a distinct layer that has been tilted and eroded, and this allows us to look at the cross-section through the layer. When we looked at the layer with our high-resolution Mastcam camera, we found that it was comprised of sand grains and small pebbles that had become cemented to form a hard layer. Here, you can see a pebble that is 3 centimeters in diameter, so smaller than a ping-pong ball. This suggests that this layer is an ancient gravel deposit. The surprising thing is that when we looked at the pebbles closely, we discovered that many of them were quite well rounded. This is very different to the many angular clasts that usually litter the Martian surface. Here, you can see a rounded pebble from a riverbed on Earth. On Earth, rounded pebbles are a common telltale sign of rocks that have been transported by water, for example in a river or stream. As water flows over a riverbed, if the flow strength is great enough, the pebbles are lifted up into the flow or rolled along the riverbed, and they become pounded and battered against each other, and this causes them to become rounded through time. So what we think we might be seeing here on Mars is an ancient riverbed with the pebble beds representing old stream deposits. The size of the pebbles tells us that these rocks could not have been transported by the wind, so it seems clear they must have been transported by water. So how did this pebble deposit get to be here? If we look more broadly in Gale Crater, we can see that there is a prominent feature that geologists call an alluvial fan. Alluvial fans are cone-shaped deposits of gravel and sand that accumulate where streams exit mountains. In Gale Crater, there is a 10-kilometer long fan formed at the mouth of a 30-meter deep canyon that is derived from the crater rim. On the fan itself, we can see evidence for multiple channels suggesting that the stream bed direction changed through time. When we look at the location of the Curiosity landing site with respect to the alluvial fan, we see that the rover landed downstream of the fan. The rounded pebbles likely represent long-distance transport down the alluvial fan. So this is really exciting news for the science team because it's the first time we are seeing gravel transported by water on the surface of Mars. This has been another exhilarating week for Curiosity on Mars and for the science team here in Pasadena. This has been your Curiosity rover report. Check back for more updates.
So this is the mock-up, or rather the test apparatus that they've got at JPL. And here's the little sample scoop. It's about the size of a tablespoon rather. And it just rotates down and scoops up loose material. And then they vibrate the end of it to shake material out of the scoop and also to get rid of any large clods that are part of it. And then once they've done that, they close the scoop up against this mechanism, and there's little tubes inside and conduits and things that they move the sample around to process. And so here's the real deal on Mars.
I'm Noah Warner, Tactical Uplink Lead for the Mars Science Laboratory mission, and this is your Curiosity rover update. Curiosity is currently at the Rock Nest location inside Gale Crater. When we first arrived at Rock Nest, we performed a wheel scuff maneuver. This is our rover's version of kicking up the dirt with your hiking boot to determine if the Rock Nest area was indeed a good first scoop target. The first scoop was successfully performed on Sol 61, and the entire team was excited to see the Mastcam images showing the scoop full of dirt, as well as the video of the vibration activities performed with the turret-mounted tools. This vibration allows the team to level out and remove any excess sample before closing the scoop, and it also provides some insight into the makeup of the soil. Any large particles would tend to float up to the top as the entire sample is vibrated, much the same way you would shake out the marshmallows in your box of Lucky Charms. Looking carefully at images, the team noticed a bright object lying on the ground just in front of the rover. We typically call something like this FOD, Foreign Object Debris. The ChemCam remote micro-imager captured a high-resolution image of the object showing that it is most likely a benign piece of plastic or shrink tube left over from a terminated wire. This could have possibly come from the rover or from the descent stage separation event during landing. Curiosity processed the scoop sample through Chimera, our labyrinth of passageways at the end of the arm that we use to sieve and portion the soil sample. We did some internal sandblasting by vibrating the sample at different orientations of the turret in order to remove any internal contamination. The team dropped the first scoop off to the left side of the rover, and in upcoming sols we will make our first attempt to drop off sample to the observation tray and the ChemIn instrument. We plan to be at Rock Nest for the coming week to complete our scoop activities, and then we'll get back on the road to Glen Elg, where we'll be looking for our first rock to drill. That's your Curiosity rover report. Check back soon for more updates.
So that's what they've been working on. And this is just the high-res images. This was after they sieved the sample, so this is the coarse stuff that's left behind. I think that's larger than 150 microns, which is, if my memory serves me right, it's like 0.008 inches in diameter. So still fairly fine stuff, but it's a lot coarser than the really fine dusty stuff that falls through a sifter like that. And then this is the sample that's collected after it's sorted. And so this is all the fine material that fills that part of the Chimera. And so all of this verifies that the whole system works. They're able to sort the samples according to size and move it through the system appropriately, and subsequently they've actually delivered the samples into the chemistry experiments. So there was mention of this bright particle that they found. This is the microscope camera view of that, and I think it's pretty clearly man-made, and the thinking is it's probably like insulation or shrink wrap that was on some of the cables that were probably ones that were cut when the descent stage was released on landing. And it's a fairly dirty activity, and almost certainly there was debris settled on the Curiosity because of that, and then as you drive along, either the vibration or the wind can blow that off. So the initial concern was, my goodness, the rover's falling apart. We need to make sure we know what this is. And after looking at it, they're relatively sure that it's just what I already described. And then since then, of course, they're very sensitive now to looking for bright stuff on the surface. And every now and then they see things like this. And turns out that's just a mineral grain that's catching the sun just right. And so it's sort of a shiny facet on a pebble or on a sand grain that makes it look very bright. And so they've seen quite a few of those. There's another one sort of peeking through and another one there that's covered in dust. Okay, so this is then early this month, the first
on the ChemIn instrument on the Mars Science Laboratory.
Experiment with the X-ray
Curiosity rover update. We've been
spectrometer.
spending time in an area called Rocknest, and this week we delivered a scoop of a dune to Curiosity. ChemIn performs what we call X-ray diffraction measurements on powdered rocks and soil samples. And X-ray diffraction is the best method for telling us what minerals are present in a rock or soil because it's sensitive to the arrangement of atoms and minerals. As the X-rays strike the soil sample, ChemIn shows us how mineral crystals distinctively interact with X-rays. And this image shows our first X-ray diffraction results. The diffraction signals appear on the detector as rings that represent the fingerprint of the individual minerals. The rings tell us not only what minerals are present in the soil, but also how abundant they are. The ChemIn data provide us with distinctive signatures of the minerals plagioclase feldspar, pyroxenes, and olivines. Peridot is a variety of olivine. Just keep in mind that the olivine in the soil sample is much smaller than these crystals. Roughly half of the soil consists of poorly crystalline material such as volcanic glass. Thus, the Martian soil appears very similar to some weathered basaltic soils that we see on Earth in places like the flanks of Mauna Kea, Hawaii. You can appreciate how revolutionary ChemIn is when you consider that instruments of this type on Earth are typically about the size of a double-wide refrigerator, and the ChemIn instrument on the Mars Science Laboratory is about the size of a shoebox. ChemIn has been modified for use on Earth in places such as Antarctica and the Arctic. It's also been applied for the detection of counterfeit pharmaceuticals around the world, and a modification of the instrument has been used in archaeological studies to help us understand the nature of the surfaces and how we might protect them. In the coming weeks and months, we're excited to measure more X-ray diffraction data on soils and rocks to tell us much more about the geology of Gale Crater. This has been your Curiosity Rover report. Stay tuned for further updates.
And then the final step here, well, sorry, I'm getting ahead of myself. They've been exercising the ChemCam, which is the system that has the high-powered laser that zaps, vaporizes spots on the rocks. And so this is an example. This is a rock that they decided to study, and I think we'll look up close right here. And so there's those cracks that we saw before, and so there's 5 spots that they vaporized in that rock. And the report from this is they determined that the rock actually had sort of 2 different parts to it. The part here on the right, this lighter colored stuff, is one type of volcanic composition, and the stuff on the left has a lot more olivine in it. So it's probably a flow of material that maybe there were like 2 flows that came together when this was made, and each one had a somewhat different composition to make that rock. And this is just a little, well, I'm not sure why that's not. I'm sorry, let me back up and see if we can get this going again. There we go. Well, you can sort of see there's a hole blasted in the sand, and that's when they try to vaporize a spot of sand. So they can use the ChemCam not only on rocks, but on the fine material of the surface. So, there we go. Okay, so final movie here, and this is the sample analysis at Mars
Deputy
experiment.
Principal Investigator of the SAM Instrument Suite on Mars Science Laboratory, and this is your Curiosity Rover update. While our robotic explorer has been busy characterizing the surface of Mars, the SAM team has also been busy, but we've been looking at something invisible, the Martian atmosphere. SAM, or Sample Analysis at Mars, is not one instrument, but 3, all of which are designed to work together to chemically characterize Mars. SAM measures chemical elements and molecules in a mass or size range between 2 and 535 mass units, And we do this by looking at gases. We can bake solid samples until they give up their volatile components or their gases, or we can directly inhale the Martian atmosphere through our inlet ports. With our QMS, SAM is able to detect the most dominant gas in the Martian atmosphere, carbon dioxide. We've not only measured its abundance and the ratio to other gases in the Martian atmosphere, but we've also measured its isotopic character. The other instruments are a tunable laser spectrometer and a gas chromatograph, the latter being used mostly to look for organic molecules in solids. Now, the tunable laser spectrometer has a special role for SAM in that it can very sensitively detect the organic molecule methane, which has been observed from the Earth telescopically and also by the Mars Express orbiter at very, very low limits in the Martian atmosphere. We're trying to discover whether or not we can see this molecule from the Martian surface and if it has any variation from season to season. In the coming months, wherever Curiosity goes, SAM will continue to sniff the Martian atmosphere, periodically looking for changes on a seasonal, maybe even diurnal basis, and that will tell us something about the dynamics of the exchange between the surface and the atmosphere. This has been your Curiosity rover update.
The
Check
significant
back for more.
result that's been released so far is they did do the sample, the analysis of the atmosphere looking for methane, and the number they came up with was below 1 part per billion of methane, which is much lower than what had been anticipated if the detections from Earth actually held up for this area. And of course, methane, the interest in that is there's really two ways to produce it. One is volcanic, and the other is you have microbes giving off methane, or cows. We won't get into that. And so if there was a high level of methane, I mean, high being, say, 10 times what they found, that could indicate that there was microbial communities living under the surface. The thing about methane is it's destroyed in the Martian atmosphere. Its lifetime is probably on the order of tens to at most 100 years. And so in order to actually have any accumulation in the atmosphere, it means you have to be producing it and resupplying it. Since we don't see active volcanism, that would lead you to the biology story. And so this will be an ongoing experiment, but at least the first pass is essentially negative. And getting back to that, the flurry of media attention, when John Grotzinger was making his statement, he was talking about the first soil sample results from SAM that they were actually repeating to try and confirm their results. And so it is expected whatever the excitement is going to be coming out of this experiment next week. So stay tuned on that. Well, I guess I lied. There's one more movie. I'm going to skip this, actually. This is talking about the meteorology experiment. They've been getting good data back. They've also been getting lots of information on the radiation field of Mars, the radiation environment, rather. And the news from that was the level of radiation they're seeing is not incompatible with having astronauts on the surface, providing that you give them some sort of shelter when they're not out working on the surface. This was one of the exciting things from the meteorology experiment. This is wind direction and the atmospheric pressure, and you see these couple of sort of spikes here. What this says is that the wind direction is changing very rapidly, and it's sort of bouncing around there, and you've got a drop in pressure at the same time. So the interpretation of that is the rover got hit by two dust devils that went probably right over the rover. We haven't talked about this for quite a while, but both Spirit and Opportunity have seen lots of dust devils. In fact, they think that's one of the factors that's been cleaning the solar panels off periodically, as a dust devil comes over and sweeps the dust away. And they've got lots of really good movies and pictures of dust devils from both Spirit and Opportunity, have not seen in any of the images from Curiosity any evidence of dust devils either nearby or in the distance. And so that's it's an interesting result. They're certainly seeing the signature here, so they're going to be trying to target some observations, looking at the horizon and seeing if they can actually visually detect the dust devils. And another thing that hit the news in the last week, this is an image from the Mars Reconnaissance Orbiter. This is a global map, and there's a fairly large dust storm that was brewing in the southern hemisphere, and this is the area that quite often spawns global dust storms when you get massive dust storms down here. Curiosity is sitting right here, Opportunity is over there. Both of them detected an increase in the amount of dust in the atmosphere, so the thinking was that we might be headed for a global dust storm. So this was 10 days ago. The most recent observations just a couple days ago indicate that the dust storm is actually subsiding. So that's potentially good news. It doesn't matter that much to Curiosity since it's nuclear powered, doesn't worry about dust collecting on it. Opportunity, on the other hand, is much more dependent, well, it's entirely dependent on sunlight since it's solar powered. And so that we would just as soon not have a major dust event because they would almost certainly have to stand down an Opportunity for a couple months until the dust cleared. And finally, the most recent thing that they've done is this new activity they call touch and go, where instead of going up to a rock and sitting there for several days, they're able to drive up, do some analysis, and then continue driving in the same day. And so this is just an animation of their planning tool that they use to control the rover. And so there it was, analyzing a rock in the front here. Now it's stowing its robot arm, and then it gets ready to drive off into the distance. And you notice it does this sort of herky-jerky motion. That's actually the way that it does things. It'll drive for a couple meters, then it sits and takes more images with its hazard cameras and makes a map of what's in front of it, and determines which way it's safe to drive. Okay, and the final thing I wanted to show you is that they got a really nice set of images, a mosaic, sort of a self-portrait of Curiosity early this month. And so this is just a view from the mast camera looking at the end of the robot arm. This is the microscope camera, and that's what they ended up using to take this other image. And so what they end up doing is holding the arm out in front of the rover, and they just pan it up and down, back and forth, and build up hundreds of separate images covering the entire rover. And there we are. And the interesting thing is, by this technique, you can't actually see the arm itself. I mean, the arm should be coming out of this, but they sort of are able to look. You get enough images that are seeing the background without the arm there that you're able to piece it together. And it's a bit distorted, but there's the front wheel, middle wheel, back wheel. There's the camera. There's the radioisotope generator. Anyway, I'll zoom in here on a couple of these. So that's the camera. And actually, if you see this on your computer, you can see the robot arm hanging out in front. This is the ChemCam, the laser system, and the mirror there is giving you a reflection of the background. And I thought this was pretty cool. This is the middle wheel on the right side. And what I notice is all these dents in the wheel. Remember, the wheel is made out of aluminum, and I think what happened is this is the part of the wheel that was down when the landing happened, and so there were probably small rocks, and the force of landing was enough to dent the wheel. So that's pretty cool. And here was an image that was returned 2 days ago. So this is the type of surface that they're wandering across right now. And we'll certainly have a lot more to talk about when we next come back. So I want to really quickly, well, I'm sorry, this is the recap here. So this is what I wanted you to notice. So far, they've returned almost 27,000 images, and that's in 112 days. Opportunity has returned about 170,000, 175,000 over 3,400 days. But you can see if we even get to 1,000 days, we're going to be up at 250,000 here. So, so it's really been returning a lot of images. Okay, so very quickly, just because I'd promised lots of people I was going to do this, this is just a quick travel log, if I can actually get to the next picture. Come on. Okay. Anyway, last month, I ended up going to Russia for 10 days to see the launch of the crew to the International Space Station. And I just wanted to very quickly go through a few of the slides from that. I'm going to do a dedicated evening lecture in February talking about this, so you'll be able to hear a lot more about this, but I'll zoom through these. So this was the 4 of us that went from Denver. Mark Ravenhill from our development office, Tony Combs, who's an ex-trustee, and George Shaw, who has a large construction company in the Denver area. And this is when we arrived at one of the Moscow airports, all looking fairly, well, I was fairly bleary-eyed at any rate after 20 hours on airplanes. But that was our first taste of Russia. The next day, we went to Star City, which is the Russian equivalent of Johnson Space Center. It's where they train all of the cosmonauts and now American astronauts that are launching on the Russian Soyuz and any European and Japanese astronauts that are going to the ISS. And this is a very, well, I'm not sure what word I should use. You drive through woods, sort of a fairly dense forest to get there, and then all of a sudden you're there. So it's not a very dramatic entrance, but nonetheless, this is where every cosmonaut since Yuri Gagarin has been trained. And this is a statue of Yuri near the entrance. So this is one of their Soyuz simulators, and you'll see Soyuz is a fairly small spacecraft. This is Tony Combs standing next to it. This is the descent module, and this is where the 3 crew members launch as well as return to Earth. Then this is the orbital module that they inhabit when they're on their way to the station. And so this is the interior of the descent module. There's 3 seats here, and this is about the size of the front seat of a Volkswagen Beetle. So it's you have to be very good friends to spend 3 days cooped up in this before you get to the space station. And this is, they have a system like this in Houston as well. It's called the Neutral Buoyancy Chamber. They've got a mock-up of the Russian segment of the space station. Here's 2 cosmonauts in spacesuits and several scuba divers supporting them. And so they use this to simulate microgravity. And here's another statue of Yuri Gagarin. He's absolutely idolized by certainly every Russian and everyone in the space program. And this is another view of Yuri. And this was one of his uniforms with all of his medals. So the day after that, we went to a Russian Air Force museum of lots of very interesting aircraft. This is the largest helicopter that's ever been constructed. It's actually got it's about 150-foot diameter wing with a rotor on each end, and it could carry something like 150 people inside, as well as a lot of cargo. So there's our whole crew in front of that. This was the Konkordsky, who was the Tu-144. It was the Russian supersonic transport. And they flew this from the late 1960s to the mid-1970s, but it was never really commercially viable. And then they terminated the use of it after one of them crashed at the Paris Air Show in the mid-1970s. And this was a Russian supersonic bomber. The nose drops so that they can actually see out of it at landing. This was our guide. He was a fighter bomber pilot in World War II. His name was Alexei, and he certainly knew everything there was to know about every one of these airplanes that we saw. And a few obligatory tourist photos. This is St. Basil's Cathedral at the one end of Red Square. This is Lenin's tomb with the Kremlin in the background. And this is the GUM department store, which is on the other side of Red Square. And unfortunately, we didn't have time enough to go into this, but it's apparently the largest department store in the world. And here was a few days later. We flew to Baikonur in Kazakhstan, which is the launch facility for the Russian space agency. And this was the Soyuz rocket being rolled out of the assembly building. There's a train that goes up and pulls it down a set of rails a couple miles to the launch pad. So there's the tail end of the Soyuz. There's a center stage and 4 strap-on boosters. You see all these nozzles. Each one of these is, each stage actually has just a single rocket motor with 4 nozzles on it. And this is, this was, to me, the launch was amazing, but this was even more amazing. So I was probably standing here, and the rocket was where the screen is, moving past. And I made the comment that if I had had a magic marker and there weren't these really cross-looking guards with submachine guns, I probably could have signed my name on the side of that rocket. But that was a really amazing thing to see, it just rolling past. And here's the Soyuz capsule embedded in this launch fairing. There's an escape system in case something goes awry in the first couple of minutes. And this is just a really quick movie showing how this happens. And we were standing essentially right there. Okay, I'm going to stop that. And this was about 10 minutes after it came out of the assembly building, our view of it rolling by. And here we are on the launch pad. There's Mark, and here's the launch pad off in the distance here. And here's 3 of us on the launch pad just to prove that we were there. And once it gets there, they have this, it's called a strong back with a piston on the bottom, and they just rotate it vertically. And there it's installed on the launch pad. And here's our whole crew with the rocket off in the background. And this was the morning of launch. This was Kevin Ford and I'm sorry, let's see, Novitsky and Taralkin were the 2 Russian cosmonauts, and so they left their quarters to get on a bus, and then about 2 hours later they were fully garbed in their spacesuits and went on another bus out to the launch pad. And there it is from our vantage point. We were about 1.5 miles from the launch pad. This is with a 200mm lens, so not quite that close, but it was certainly a spectacular view. And I've seen, I think, 9 shuttle launches. Each of those were about 3.5 miles away. So much, much closer view here. And we were with the families of the American astronaut and the 2 Russian cosmonauts. So there was a group of about 100 people in total watching this launch. And here's the close-up view from NASA TV.
7, 6, 5, 4, 3, 2, 1, and ignition. Liftoff. Liftoff of Kevin Ford, Evgeny Tarokhin, and Oleg Novitsky as they head on a 2-day trip to the International Space Station. Seconds into the flight. Good first stage performance. The Soyuz delivering 102 tons of thrust from its 4 boosters and single engine. The first stage of the Soyuz measures 68 feet in length and 24 feet in diameter. It is burning liquid fuel for the first 2 minutes and 6 seconds of the flight.
Okay, we're running very late, so I think I'm going to stop it at this point. But at our 60 Minutes in January, I'll give you the date. I think it's the middle of February. I'll be doing a dedicated evening talk about this whole expedition. So I'll end it here. Our next 60 Minutes is going to be January 30th. We're going to skip December, and I'll wish you all happy holidays and happy New Year's. And I think I'll give everyone, since we're so late, I'll give the folks that need to leave a chance to do that, and then we'll have our question and answer with Dimitri and myself. So thanks again for being here, and happy holidays. We'll see you next year. So I should yell at Dimitri for being long, but I have to yell at myself for being even longer. So I apologize for the length of the program. I don't actually know the answer to that, but this seems to be a common thing for the Russians, because the Atlas V, which uses a Russian engine in the first stage, has 2 nozzles on a single motor. So I think it's okay, and let us know next time. Okay, why don't we try to answer a few questions anyway, and then we'll really call it a night. Yes?
Yeah, so the question is, what is doing the annihilation when you have annihilation of dark matter? And so one presumes actually that the dark matter that was formed in the early universe, that, the WIMP miracle thing, was, in essence, can be equal parts of matter and antimatter of that dark matter particle, whatever it is. Say it was the Higgsino. So when that Higgsino comes together with its anti-Higgsino, when they annihilate, they actually produce 2 gamma rays to do that. Same mechanisms as a positron and electron come together and form 2. And they're part of the same particle family, so there's no reason they can't produce those, the photons in the ordinary light, basically. I haven't heard any of the proposals that can be like they do suspect it to be one dark matter particle, and that was another interesting thing I had taken away from the meeting was like, you know, is there a whole family of them or whatever? They really do think it's one particle. It can actually be, but so I put up that list of all the fundamental particles, all the quarks and stuff and everything. They all have their antiparticles that we know to exist. Our universe is made mainly of the matter particles, and not the antimatter particles. But there are some particles that are their own antimatter particle, and I think the Higgs particle can be its own the Higgsino, it would be the Higgsino and the anti-Higgsino. So so that can actually happen. Cool.
Okay, I'm trying to wrap my brain around this, but the one slide you had showed that more than half of the matter of the universe is dark energy. How can energy be matter?
So yeah, I didn't want to get into dark energy. So from a dark matter standpoint, dark matter outweighs ordinary matter by like 4 to 1, and then the rest of this stuff's called. It's given the term dark energy. It's not the same as when we think of the equivalence between mass or matter and energy. It's not that same energy term. So the dark energy is what's responsible for causing the universe to accelerate. So if I had a cubic meter up in front of me here, 75% of what's in there is this stuff called dark energy that we have no clue really right now what it is. We only know how it is affecting our universe.
Steve, I was interested, the rocks that are rounded, it seems to show that there's a flow, but you said like a constant flow in the past, like it would have been a running river?
Well, so the question is my comment that it was a sustained flow that would round these rocks and pebbles. It doesn't necessarily mean that it is constant. It's like a river that's flowing for years and years, but it does mean that it's more than a single episode. So it's not just a gush of water that lasts an hour and carries these rocks downstream. It has to be, potentially it could be a gush, and then a year later you get another gush, and a year later you get another gush. But it's something that's happened at least repeatedly, if not for a long period of time. And that's because it takes many, many collisions to round off those rocks.
So there could have been a whole bunch of gushes moving these things maybe 30 miles or whatever to get them rounded as they go.
Right. It could have been, it could have lasted for years. It could have been episodic over many, many years. The result is the same. But regardless, that's the first time we've seen that on the surface. Yes?
Could the source be some of these icy comets that make the craters and melt after they hit?
So could the source be comets, or, well, that could be the source of the water over a period of time, not necessarily the source of the flow. It could be that the climate is, the environment is warm enough that whatever water is there in the form of ice would melt. It could be an impact that melts all of the ground ice. It could be rainfall. Could be many things. But at any rate, it's the first time we've seen that type of material on the surface. We've seen evidence for it from orbit, but not close up. In the back.
Curiosity traveled any distance?
So has Curiosity traveled any distance? And I think it has gone at this point about 600 meters from the landing site, 600 or 700 meters. This Glen Elg target that they're moving toward, I think, is about 850 meters from the landing site. And they should be there by Christmas time is what the teams are saying. And then they're likely going to be sitting there for several, probably at least a month and a half. So quite a few weeks once they're there, and that's the point that they're going to be analyzing a lot of rocks. Glen Elg looks like it's the joint of three different types of terrain. They've got this alluvial fan material, they've got what looks to be volcanic material, and they've got whatever it is that they're sitting on right now that seems to be abutted in that area. And so that'll give them the opportunity to look at three very different types of terrains. Once they've done that and verified all of the all of the instruments on board are working properly, then that's the point that they'll start driving off toward Mount Sharp. And that'll be sometime February, March of next year probably. And then it'll take them probably the better part of a year to get to Mount Sharp. And that'll be the real exciting stuff once they start climbing that mountain. Okay, I think we should call it a night. So thanks a lot, and we'll see you next year.
I was going to ask you a question. Do they sedate? Do they take some sort of sedation to last 2 days in that cramped space?
Well,